Welcome to Excel and Business Math video number 44. Hey, in this video, we got to talk about present value of a lump sum amount. Now, what in the world does that mean? Well, being able to calculate with this formula, the present value of a lump sum, will allow us to answer this question. How much do I need to deposit today to be a millionaire in 30 years? Notice in this question here, $1 million in the future is known. And what we need to calculate is the present value, meaning how much today do I need to put in the bank as some deposit to be a millionaire in 30 years. Now, the cool thing about this calculation, this present value calculation, is this looks pretty similar to the formula we used last video for future value. And here's the concept. Present value, that's the amount today. Future value, that's the amount in the future. So if a bank pays 10% and we have $1, well, it will grow in 1 year to $1.10. So notice what we do. Here's the present value. We add the interest to get the future value. That means the future value of $1 going this direction, adding interest through time, is $1.10. Well, guess what? We can do the reverse. Instead of going forward in time, we can take $1.10 that we're going to assume we get in 1 year and do the reverse. The present value is $1. Now, what does that mean? This way, we added the interest, and the calculations we're going to do for present value will be subtracting or taking out the interest. Now, before we go over to Excel and start calculating, we want to go look at our PDF notes. Now, both the PDF notes and the Excel file can be downloaded from the link below the video. Now, we're going to look at a future value example. This is exactly the same example we did last video. We'll start with this, and then we'll try and do it in reverse to get to the present value. Now, here's the first example for this video and example number 5 from last video. If you deposit $125,000 in an account for 35 years that pays an annual rate of 5% compounded quarterly, what is the future value? Well, we list all of our variables. And by the way, these variables will be exactly the same for present value and for future value. If we used our math formula, we would do all the calculations, substituting the variables in, and we'd get $71,564.83. If we used our excelfv function, we'd plug these in and get exactly the same number. Check. But this is the timeline. From 0, that means we deposited $125,000 and we waited for time. The years ticked by, and as time moves forward, we were adding interest. So in 35 years, there's the future value amount. The difference between future value and present value, that's the interest, $586,564.83. We moved forward from the present value to the future value, adding the interest. Now let's go to the next page. But what if we wanted to do the reverse? We knew the future value that we wanted, and now we want to solve for the present value. There's our formula right there. Without even getting a different formula for present value, well, we could just plug the numbers in. So if we knew we wanted that amount compounded quarterly at 5%, notice we can just plug the numbers in. There's the future value. There's our annual interest rate, number of compounding periods per year, and total number of periods. We just plug everything in, and guess what? That PV is what we need to solve for. That means that PV is going to be the amount to deposit in the bank today to get that future value amount. What we need to do is the reverse. We know this, and I need to go backwards and try and figure out that. Now, we already did this example, so we know both of these numbers. But now we're going to try and just use this number and our 5% and other variables to calculate what the present value is. Conceptually, there's the full amount. If we need to put some amount in the bank and it was to grow earning interest moving forward, That means we need to go conceptually backwards and take all assumed interest out of the future value amount to calculate the present value. We need to somehow go backwards to get to that number. On page 5, there is our present value math formula. There's the Excel function. Instead of FV, it is PV. And look at that. We put the rate MPER. And instead of putting a cash flow present value in our future value function, now we're going to put the cash flow amount future value into our PV function. Here's all of the math variables. Here's all the Excel variables. Now, for our math formula, we would write it on paper like this with a big division bar, and then everything in the denominator would be calculated separately from the numerator. When we type it into Excel, we can type it left to right like this because that division will not be calculated before exponents. Remember, our order of operations, everything in parentheses first, then exponents, then multiplying and dividing left to right, and then adding and subtracting left to right. Now, if we go to the next page, here's our example that we'll do just in a second in Excel. If I were doing it on paper, I would plug in all the numbers and calculate. In Excel, I use the PV function, and Excel will know cash flow. So if we put the future value that we want to withdraw as a positive, PV function will be polite and give the answer as a negative because it's coming out of our wallet and into the bank or some investment vehicle. And the concept for our first example, moving forward from present value and calculating future value, that's when we add all the interest to get to future value. When we're starting with future value and trying to figure out how much to put in the bank at time 0, we're going backwards. It's as if we're subtracting out all of the interest that we're hoping to earn. Now let's go over to Excel. All right, on the sheet FV, this is the example we did last video where we started with a present value of $125,000. We put it in the bank and we calculated our future value. Now let's go over to the sheet PV2. And here it is. If you want $711,564.83 in 35 years, and there's a savings account today that offers APR, annual percentage rate of 5% compounded quarterly, what is the present value or amount you need to deposit today to get that future value amount? All right, so future value amount, we know that number. So I'm going to type it here. Enter, enter. The cash flow direction, well, this is in the future. We're hoping it's going to come into our wallet or purse. So that's going to be a positive for our Excel function. The annual rate, also known as a discount rate. Now, when you're calculating present value like we're going to be calculating, you might hear annual rate. You might hear rate of return. But commonly, you'll hear discount rate. All of those are synonyms that mean what's the annual rate. So the annual rate, 5%. Compounding periods per year, that's quarterly, so we use a 4. Years, that's 35. Now we can calculate period rate. Equals, there's our 5% divided by our quarters. Enter. Total number of compounding periods. Equals, that's going to be our total years times number of compounding periods per 1 year. And enter. So 140. All right, our present value calculation, if we're using the Excel function, equals PV tab. Look at that. It looks exactly the same as the future value. But behind the scenes is programmed to calculate present value. So the rate, that's the period rate, comma, NPER, total number of periods, comma. We're skipping payment because this is a lump sum problem, comma. Future value, that's a positive number. We don't need type because that's associated with the PMT argument. As we saw last video, we simply leave it off, and we make sure and type that extra comma for PMT. We're leaving it out. We're skipping it. Next video, we'll see how to use that argument. And that argument, of course, is when you're putting money in regularly. All right, so there it is. Present value and enter. It says, hey, 125,000 out of our pocket and into the bank. Now I am going to round this. It meets all the conditions for rounding. We're dealing with money. We have extraneous decimals past the penny position, and we're going to use this calculation in a subsequent formula. So I'm going to round it, comma, to rounding to the penny, close parentheses, and enter. Now the total interest, future value minus present value. There's our future value. And since there's already a minus there, I'm simply going to add it and enter. Now I'm definitely going to check the present value. And this will be the first time we've done our math formula. Equals, well, I'm going to take future value. And now we're going to divide by, in parentheses, 1 plus period rate, close parentheses, caret. That's our exponent to 140. That will calculate perfectly because Excel will know to calculate exponents before division. And for that matter, it'll know to do the adding first, even before exponent and division because of the parentheses. So when I hit enter, there it is. We've checked and verified the present value is correct. Now let's go look at our next example. I'm going to go over to the sheet PV3. If you wanted to have $1 million when you retire in 40 years, how much would you have to invest today if you could earn an annual rate of 10% compounded monthly? Now, I put the values here, the future value, we know that. Years, 40 years until retirement. Annual rate, we're assuming this. Now, notice it says how much you would have to invest today. Now, investing means anytime we're putting some money somewhere, hoping to earn a return. Now, in this class, we're talking about simple things like savings accounts or CDs or debt contracts where the actual interest rate is defined by a contract. If you went out and invested to get this $1 million in the stock market, in a proper finance class, we talk all about that. But we're going to assume that the annual rate in whatever investment we make is 10%. And actually, historically, if you invest over long periods of time, like 40 years or 10 or 20 or 30, 40 years, 10% return is not uncommon when you invest in stocks. All right, so we're going to calculate our period rate equals, there's the 10%. Divided by our 12 periods per year and enter. Total number of periods, there's 40 years times 12 months in each year and enter. So 480 periods. The present value, that will be equals PV. The rate, that's the period rate, comma, NPER, total number of periods. Comma, we're going to skip the payment. Next video, we'll get to finally use that argument. Comma. The future value, that's that $1 million we're hoping to have in 40 years. We don't need that last argument, so simply close parentheses and enter. You've got to be kidding me. 18,000? Yes, the variable that has the most influence on the accumulation of interest on interest is time. That is a long time to leave your money in some investment vehicle. So although it grows to $1 million, it looks like it started out just at a little under 19,000 bucks. Now I'm going to round this. We're going to round it to the penny, comma, to close parentheses. Now the moment of truth equals, and there's our future value, plus, because we already have our present value as a negative, and enter. That is a lot of interest. That is the power of compound interest. Now let's check the present value equals. There's our future value. That's going to be in the numerator, so I divide. In parentheses, 1 plus the period rate, close parentheses, caret, and there is our 480. When I hit enter, there it is. We've checked. $18,621.74. I put that in the bank. I leave it at an assumed annual interest rate of 10% compounded monthly for 40 years, and there it is, $1 million. Now I'm going to check again with the future value formula equals. Well, to get future value, we have to take the present value times, in parentheses, 1 plus our period rate, and we raise it and we raise it to 480 periods and enter. Look at that, $1 million. Now let's go look at our fourth example, PV4. If you wanted to have $250,000 for your daughter's college education in 15 years, how much would you have to invest today if you can earn an annual rate of 5% compounded monthly? Well, there's the future value. So in 15 years, when she's ready to go to college, we want to have that much money. So how much do we have to deposit today? Years, annual rate, number of compounding periods per year, equals, to get our period rate, annual rate divided by 12, and enter. Total number of periods, years times months, 180 periods. So the present value equals PV, our rate, period rate, comma, NPER, total number of periods, comma, comma. And as a positive value, we're going to enter in future value. Close parentheses and enter. Now, we're actually doing all of our calculations from an investment point of view. If we were doing it from the bank's point of view, then, of course, the bank would have to pay this out in 15 years. So that would be a negative to them, and that would change the result of the present value. That means the bank would receive from the investor $118,275. Now, I'm going to remove that minus because we're doing it from our point of view. We are depositing that amount, and there it is. We deposit $118,275 and 79 cents, and in 15 years we will have $250,000 for our daughter's education. Now I'm going to round this F2, round, comma 2, close parentheses, and enter. Total interest earned. I'm going to take future value plus this minus, same thing as subtracting, and enter. That's a lot of interest. We'll check with our math formula. There's the future value divided by, in parentheses, the period rate, caret, and there's our 180, and enter. I'm going to check future value. Hey, there's the present value. If we put it into the bank and an assumed 1 plus that period rate, and raise to our 180, and enter. And I exactly get 250,000. All right, let's go look at our last example for present value on PV5. Now on the PV5 sheet, we want to look at a future value of 700,000 at 5%, interest paid quarterly, but we want to adjust the year variable when we make our present value calculation and see what happens when we're trying to save up for 700,000. What happens to the present value when we increase the years? Well, of course, the longer we have to wait, the smaller the amount we have to put in the bank today to get a given future value amount. All right, so our period rate equals annual rate divided by number of compounding periods. Tab. Total number of periods, I'm going to take years times number of compounding periods per year. Tab. Equals PV tab. The rate, that's the period rate. So there it is. Comma. NPER, that's total number of periods. Comma. We don't have any regular payment of cash. Comma. We do have a future value we're trying to save up for. Arrow over to get as a positive number 700,000. We do not need type, close parentheses. Now when I hit enter, I'm going to highlight all 3 cells, double click, and send it down. And look at that. If we're trying to save to get 700,000 and we're waiting for 15 years, we have to put about $330,000 in the bank. If we can wait for 20 years, all we have to put in is 259. And you can see all the way down to 50 years, we're trying to save up for $700,000, and all we have to do is put 58,000 in. That illustrates the power of the time variable, the total number of periods, and the power of compound interest. So, for example, we can clearly see it's over $600,000 of interest that we earned if we can wait 50 years. About half of that, $700,000, if we only can wait 15 years. Now, I'm going to double check this equals, and there's the future value, divided by in parentheses 1 plus. There's our period rate, close parentheses, caret. And there's our total number of periods, tab. Now, the moment of truth, the interest, equals, and I'm going to go get the future value, and I'm going to subtract by adding our negative amount from our PV function. And now when I highlight these, I'm going to copy them down. That is simply amazing. The power of compound interest. That time variable has a huge impact. All right, so we saw a bunch of examples in this video about present value. There are some awesome homework problems for you to practice, 6 of them over there. And before we end this video, we want to go back over to our PDF notes. And we actually want to talk about the fundamental truth in finance. And that is a dollar received today is worth more than a dollar received later. This is true because of interest. Well, wait a second. Here it is. The question is, would you rather receive $1 today or wait 1 whole year and receive that dollar 1 year from now? Well, of course, you want to take the dollar today because you can immediately go out and invest it. If you earn 10% on an account for a year, that would grow to $1.10. That means you could now compare this amount to the dollar you will receive in 1 year. That's why a dollar received today is worth more than a dollar received later. The power of earning interest. And we want to end this off by reminding ourselves present value and future value. As we move forward from $1 to $1.10, we're adding the interest. Moving forward to calculate some future value, we're always going to add the interest. Going backwards, that means we know the future value and we want to calculate the present value. We are going backwards. Forward, we're adding interest. When we add interest, we're trying to calculate the future value. When we're subtracting out the interest, we're going from future value, and we are calculating the present value. All right, so in this video, we saw an example where we were saving up for a certain amount for our daughter's college education in 15 years. Over on PV3, we talked about wanting to be a millionaire and figuring out how much we had to put in the bank today. And we started off by doing the same example we did last video, but we did it in reverse. Knowing what the future value was, we went ahead and calculated the present value. All right, if you like that video, be sure to click that thumbs up, leave a comment, and sub, because there's always lots more videos to come from Excel is Fun, including our next video, 45, where we'll finally get to see not just a lump sum future value, present value calculation, but we'll be able to use what's called an annuity and put money in each month or each period and save up for some future value or calculate some present value. All right, we'll see you next video.